So, well, I didn't get a microphone, so can people hear me? What, really? What's wrong? Okay, so, well, it's interesting. I looked online and I counted them up. This is, I think, the 29th CTEQ school. And the first that's been held here at Stony Brook. So it's a little bit, it's on the one hand, it's very normal for me to talk at CTEQ schools. I don't know, I guess I've attended probably the majority of them, but the first time here at home for me. So this is a special pleasure, and thanks to Fred and to Alexi and of course to Ave, from whom we heard, for making this possible. It's certainly in that period of time when we started out, there was no real idea of an electron-ion collider. And now to have the possibility that in the future it will actually be practically in the neighborhood of Stony Brook, it's very exciting for those of us who are local, but it's exciting physics, of course, that is driving this. And I was asked to give some lectures to start things off. And so the title that is suggested by the suggestion is Deep Inelastic Scattering and Collinear Factorization. So that's what I'll be talking about. My lecture today is a lot of very basic and some of it quite intuitive ideas. And then what I have notes for in the coming lectures will be perhaps a little bit more technical, talking about how factorization is proved, what it means to prove factorization in QCD, and also about this, the first basic evolution equations, the so-called DGLAP evolution, and trying to give you an idea for those who haven't seen it of really how one calculates something in using perturbative QCD in a case where the whole world is not perturbative. The world is very non-perturbative, and finding the techniques of perturbative QCD, which after all are the things that are most closely related to the what we see as the fundamental Lagrangian of QCD, is something I think that's interesting. So, of course, also there can be some modifications, and we have the evening discussion sections in which we can talk about things that, you know, are not yet on the slides. Okay, so I have a bunch of slides, but the numbers down here, and when it gets to about 35, then we're getting towards the end. Okay. So here it is, deep inelastic scattering, collinear factorization. Here's some old references that are on there where you can find much of what's on here, but not everything. Okay, so again, what are we talking about? Well, the context of QCD is fundamental interactions. This is just to set the whole thing up, is to remind ourselves electromagnetic interactions were certainly among the first to involve the analysis after the development of classical mechanics. Plus the weak interactions gives electroweak, and then plus QCD, the strong interactions. I mean, it's not that long ago when a theory, really viable theory, QCD, was written down for the strong interactions. And together with the electroweak, it gives us the standard model, of course, plus whatever it is that we're all, let's see, here's the thing. Yeah, plus, well, we don't know what gives gravity and the rest. But from a historic point of view, QCD is a theory that's off to a good start. I mean, to some extent, one says, well, this is the established theory of the strong interactions. But in some sense, Newtonian gravity was the established theory of classical gravity when classical was all there was. But nevertheless, it's a theory that's still being discussed and developed today. So in some sense, the analogy I like to draw is that starting with Newtonian gravitational interaction, it immediately gave elliptical orbits. And this was just amazing. There are Kepler's laws, right? Derived from some very, very simple concepts. But within a very short time, people began to realize that there were fundamental things about classical gravity that could not be easily understood in terms of the kind of analysis that gives the elliptical orbits of the planets. And in particular is the three-body problem, the moon, the sun, and the earth, never mind the other planets. It was very early, in a matter of 20 years, without an internet, that people realized there was a fundamental problem, which was the stability of the solar system, which is still being studied today. Well, QCD is off to, in some ways, an analogous start, starting with the QCD Lagrangian of the form of quarks interacting with the gluon field, and then being Dirac quarks for the most part, plus the interaction of the gluon field itself, a generalization of Maxwell's equations, which I might say was developed just a few miles from here in Brookhaven Lab, in the famous paper of Young and Mills in 1954, right on the site where the EIC will be. Well, anyway, it was realized after a while that this gave the property of asymptotic freedom, which helped explain a qualitative feature called scaling that we'll talk about in a little while. But of course, really in the middle of all this, there are issues of confinement. The fact that we don't see the free quarks that are supposed to be at the basis of our QCD Lagrangian, or let alone the gluons. We have to do something to try to infer where those things are coming from. So to some extent, this confinement of QCD is the analog of the three-body problem in Newtonian gravity. And its history repeating itself in some way from an intellectual point of view. And that's partly what makes all these things exciting. So let's see. Now here's the one to, yeah, here we go. So here in this morning, okay, I will now illustrate, as you get older, the biggest mistake that speakers make, which is they get to their outline and they spend half the talk in the outline page. So I'll try and keep it to a third of the talk. Okay, so we'll really quickly remind ourselves about nucleons and quarks. We'll talk about deep inelastic scattering, and really the main part of today is to talk about structure functions and scaling and related ideas, and factorization I really should have put here. And then at the end, if there's time, this morning we'll talk about the classic so-called parton model extensions, fragmentation, and Drell-Yan, which I believe that Ian Stewart will talk much more about. So what we'll do is introduce concepts and results that predate QCD, led to QCD, and were incorporated and explained by QCD. Now, okay, the other thing is, please interrupt with questions. I will be so grateful. Okay, so real quick, reminding ourselves from nucleons to quarks, right? So proton and neutron. It was actually Heisenberg, and as early as the 1930s, who realized that there was a way of thinking about the proton and neutron as being, on the one hand, extremely distinct. They have different electric charge and slightly different mass, but in many ways, they're siblings. And the way that he describes things in terms of asymmetry, proton and neutron, and if one could neglect electromagnetism, the two are indistinguishable and could be transformed, the one into the other. So these are ideas, of course, are quite familiar. Then as time went on, one discovered the pions, which again are almost degenerate, not quite. Well, the pi plus and the pi minus are degenerate, result of CPT symmetry. But the pi naught slightly different, again, differing in electric charge, and described in terms of this same property of isospin. Here, isospin 1/2, as though it were like the description of the rotation group. The isospin, the actual transformations are the same as in the rotation group. And for the pions, the isospin of plus or minus 1 for the charged pions and 0 for the neutral one.
I have a question.
Yes, the question is happening up here.
So how that assumption or that approximation is good to what percent?
Well, it depends. The question is, how good is the approximation that the proton and the neutron are degenerate, or in some sense equivalent? And from the point of view of the masses, it's quite a good approximation. You can see the masses here. This may not be the only or the most relevant measure. Partly the measure is their interactions, but their interactions, say with the pions, are very well given by this. And that's the basis for the so-called chiral perturbation theory, which I won't talk about really in these lectures. But this symmetry is very, very powerful. And in fact, it was almost the only thing one had until the creation. But again, you see these masses here differ by 1 MeV out of 1,000. Okay, so here is a picture of this idea of isospin space. It's a globe. And we sort of can imagine that somebody said, oh, I mean, forgetting about the sun for the moment, that the proton is the North Pole. The neutron is the South Pole. You get from the North Pole to the South Pole by emitting what we call a pi plus. And you say, well, why do we pick the North Pole? Well, we picked the North Pole because there's something out there in the world which is not part of the globe itself, but which distinguishes different parts of the globe. And here we can think of that as the North Star. Okay? So the proton's looking up at the North Star, the neutron is on the other side of the globe from the North Star, and we get from one to the other by emitting these bosons, in this case, the scalar or pseudoscalar pion. And the analog is the rotation group. So the SU2 rotation is just like the three-dimensional rotation group in this respect. More specifically, it's the group SU2. So this was all very fine, but where did it come from? Well, the next step in this telescoped history is that the pion and the nucleons, here the proton neutron denoted collectively as capital N, not an integer. They have a common substructure, that's the quarks. This was Gell-Mann and Zweig independently in 1964, which was actually one time, well, Zweig gave a talk actually in the neighborhood here. And he talked about that he was Gell-Mann's student, but Gell-Mann went to CERN on sabbatical. So every week he talked to Feynman once a week. And Gell-Mann in CERN and Zweig, the student at Caltech, both independently invented the thing we now know as quarks. So it's kind of a neat story. But in any case, the quarks have spin, they're Dirac fermions, spin 1/2. They have that same isospin 1/2, connecting the U and D quark, but another quark, and this one, the strange quark, that's the one that really was the essence of discovering the quark model. Okay, it was really seeing the states that were available with this property of strangeness, and how difficult under some circumstances it is to get rid of the strangeness that led to the development of the quark model. And here they have approximately equal masses, although the strange quark is somewhat heavier. And here are the properties that I think we know. The U quark 2/3 of the positron charge, the D quark -1/3, the strange quark -1/3. But in the isospin, the U and D have this I3 of 1/2 and -1/2, and I3 of 0 for the strange quark. And here are these familiar combinations, UUD for the proton, UDD for the neutron, UD bar for the pi plus, and so forth. This is not, I mean, this is by way, I think, of review as a kind of warm-up. So this is the quark model. And it's this itself, reminding ourselves. So the quark model, nucleon. So you say, well, the nucleon is say, 2 U's and a D. It has a symmetric spin and isospin wave function. Return to this in a second. And an early success was that it gave, in terms of the magnetic moment of the proton divided by the magnetic moment of the neutron of minus 2/3. And this turns out to be good to a few percent. This was a tremendous success. It was a kind of mini elliptical orbit success. It said, hey, there's something to these quarks. You can make wave functions out of them and talk about their symmetries that really make sense. Of course, yes.
So what percentage is that? How good was that in terms of percentage?
I don't, honestly, I don't have available, but it's a few percent. I mean, it's really much better than, I suppose now one can calculate these things on the lattice and see indeed that this is the case, but in the theory, the fundamental theory, but I don't think a real explanation of why it works so well has been given, but it does. And well, in any case, now the idea of quarks, using all the kind of things that we're going to talk about as the hour goes along, is now just the 3 light quarks, which are the original quarks of the quark model, and 3 more heavy quarks, the charm, the bottom, and the top, that complete the list of quarks in the standard model. And all of these, except for the top quark, the very heaviest, which is really heavy, 172 times the mass of the proton, but all of the others form bound states of the quark model type. So quark model is useful, but it doesn't show everything. And in fact, the discovery of exotic states at CERN and elsewhere has really revolutionized this topic again, where there are states that can't be simply described, heavier states, and of course, unstable, that can't be described entirely in the quark model. So the idea then is we have the quark model. That's it for the quark model in this lecture. We think of now we're going to make the transition to quarks to the familiar term, I'm sure to everyone, which is partons, quark to parton, seeing quarks. Now, immediately people say quarks, you know, in these charges, 2/3 minus 1/3. It was one of these, well, is it really worth it kind of moments. But, you know, it had some successes and helped organize most of, oh, by the way, one of the things, of course, was a bit, you know, in any case, Zweig, when he recounted, he said, you know, there was something which eventually evolved into the particle data group list of particles and particle properties. And that list at the time, which was like 1960 something, was a page long, and about 1/3 of the entries were wrong. Okay, so it was, you know, it was there, but it wasn't that obvious. All right, but in any case, people went out very early and looked for fractional charges. And indeed, this is something that still goes on today, but none were ever seen. And this is what we call confinement. So quarks are there, but they're confined. So this, and then the question is, what does that mean? Will we ever have a theory of that? And well, that's what we're going to do. So a question.
Yes. Okay. Something that's long kind of confused me is that quarks exist. The quarks were, we say quarks only exist in bound states, but then we have the top quark, which decays before it forms a bound state. So when we detect a top quark, are we seeing an individual quark?
So the question is, quarks are confined, but the top quark decays. So we see it directly, and that's the beauty of the top quark. One of its many beauties. It is truly not. So what does it mean? We see effects of the other quarks decaying, but the statement is it is correct to say that the top quark exists only as a quark, which really means it just doesn't have the confinement is as we'll discuss a little bit, a long time phenomenon. It takes a while for 2 quarks to get together. I mean, a while from the quark point of view. From our point of view, it's not so long. To have many interactions, enough interactions to know that they're able to form a bound state. Okay, so these energy differences are really rather small. We say, well, how long does it take? Well, it's something like the mass of the pion or so. Can exchange a bunch of gluons and or ions or whatever to form this bound state. So it's something like a time of order h bar c over 100 GeV, 100 MeV, several hundred MeV, okay? So it's something along the times of a Fermi times in time, what is that, distance divided by c. So it's like a really short time, 10 to the minus something 20 something seconds, but the top quark decays much faster than that because it's so heavy. There's this huge amount of phase space. See, that's the thing that happens. What happens, and this will occur again when we talk about deep elastic scattering, what happens in that drives the way quantum mechanical processes go is you go to larger and larger momentum transfer and more localized in space and time interactions, is that the counting of the number of available states begins to drive the calculation. And as you go to higher momentum transfers, you have more and more states. It's just the same counting of states that you do when you do like from statistical mechanics, the number of states and the max that drives the Maxwell distribution, Maxwell-Boltzmann distribution. Same thing happens here. With the top quark, it's got 172 times the mass of the proton. It has a huge phase space of states, even though it's decaying into only two particles, say a W and a bottom quark. And that's what makes that decay rate so fast. So, all right. So the question then is, we have these quarks with fractional charges. Could such a particle be detected? So the idea was to look a little closer and do high energy electrons. So the question posed, take high energy electrons. So the thing about that is you have to have high energy electrons. That was technology. Okay. Technology, from the point of view of just sort of electronic stuff, was being developed after World War II and into the 50s and 60s, much of the technology being driven by commercial interests and consumer goods. But people began, semiconductors and using quantum mechanics to understand how you can develop beams and also how you can get large magnetic fields and accelerate things. I mean, of course, the biggest acceleration of electrons was in the old TV tubes, which were also being developed at the same time. So as technology advanced, it suddenly became possible to think about very, very high energy electrons with energies larger than the mass of the proton. Kinetic energy is larger than the energy associated with the rest mass of the proton. And this led in SLAC in the late 1960s to do what you might call a Rutherford prime experiment, where very, very high energy electrons were shined on nucleons. Pardon me a moment. Take a sip. And so here it is. The electron comes in, and we'll use this notation of momentum K. And the idea is it going to bounce off something like a quark that's inside the, here's the proton. Proton, for us, this is a simple model of the proton, also known as the circle. But because, that's kind of what it was, And so the electron comes out with some momentum K prime, and it's lost some energy, and we'll talk about how people quantify that. And the question is, will something come out? I mean, until you really did the experiment, you might say, hey, so an up quark will come out, it'll have charge 2/3. Well, it wasn't quite that simple, but something like that. So we're trying to look for point-like constituents. If there aren't point-like constituents, you won't expect to find very many electrons coming out with a large momentum transfer, just because of the of the uncertainty principle. You have to have an interaction. Large interaction has to occur really local. Okay, but if there's nothing there to interact with, you know, it's a big disappointment. So, or you're really happy because you have another picture that says there shouldn't have been anything there. All righty. Now, the neat thing about this is that the angular distribution, the difference between K and K prime, which here is well, there's first of all the question of what's the energy of your outgoing electron, and then the distribution of angles at which the electrons come out after they scatter, assuming they did. So the angular distribution gives information on the constituents because that was what could describe how the electron bounces off these little green circles. They were not thought of as green, but just to make them. So here's the kinematics. That is the basic kinematics from SLAC in the late 60s, and it's the basic kinematics for the electron ion collider. So it's yeah. So these are the notation that people often use. So here's a different picture. Proton and the electron comes in, and here this V here just means a vector particle. For SLAC and for much of the EIC program, this will just be a virtual photon. Single photon will be exchanged. It carries momentum, which is generically called Q. And the simplest thing would be that we have an elastic scattering of some constituent of the proton with a fractional momentum X of the proton momentum P. So XP goes into some P prime, which is XP plus Q. So the Q is a local emission and then a local absorption of this single photon to give a new particle, which is P prime, which is XP plus Q, not going in the same direction as the proton. Here we're thinking of this in terms of a kind of center of mass frame where both the proton and the electron are moving towards each other. And well, generally speaking, if V is a photon or at higher energies, a Z naught, this is called a neutral current interaction. Because the currents we're thinking about are the electric current of the electron and the electric current here of this quark, which is the constituents of the proton that we're after. And then also at high energies, one will see things like exchange of charged vector bosons, a W minus and the W plus, and then an electron can turn into a neutrino. You can also have muon beams, turn them into neutrinos. These are charge currents. This won't be particularly the topic that we'll be discussing today. So there's another object, which is, or a quantity, which is of basic interest. It's often denoted by W. It's W squared is the momentum of the proton plus the momentum of this exchanged photon, and that's P plus Q, the quantity squared. And here, that's the invariant mass of this whole new system that we have here. This system is a strongly interacting system. Here we can look at the electron, it can come out with, as it says L, because this could have been a charge current interaction in this general form. But if we can observe this, so in particular, if it's not a neutrino, momentum K prime, we know all we need to know. We know what Q is. And then once we know what Q is, we can add it to P and get this W squared. And this is the strongly interacting system. So this system here is really different. Some of the energy has been taken from the electron and given to a system whose invariant mass can be made much larger than the mass of the proton. And that goes by the name of deep inelastic or deeply inelastic scattering, DIS. Whoops, did I have an 11 here? Oh yeah, so here, the idea in this picture is often described by what is called a parton model. And the basic parton model relation, and this is really where we begin to get into the ideas that are the ideas of perturbative QCD and the analysis of high energy interactions, not only at deep and elastic scattering, but also at hadron colliders. But we start with a basic part-time model relation here at the top, which is something which is really surprising. It says the cross-section, inclusive cross-section at very, very large Q. So by inclusive, what do we mean? Let me go back to the picture. No, going back is this way. Oh. Here. All right, going back to the picture. Here we are. All right. What we do is in the inclusive cross sections, still, yeah, here we are. We say, okay, remember if we observe this outgoing electron, we will know what the momentum Q is. And so we know what the invariant mass of this system is, but we don't know what it consists of. So we do the experiment a lot of different times. I mean, originally, all we had to do was look for the electron rather than looking into the details of the system. And once we sum over all the hadronic states, we call that an inclusive cross-section. Okay? And the inclusive will matter a lot. Did I? No, somehow or other, oh, I keep. All right, so we saw this. Oh yeah, so we will. Is this the next one? Yes, it is. Good. It actually makes sense that it's the next one. So here's a little bit more about the typical notation that one uses and encounters in discussions of deeply inelastic scattering. So again, Q, capital Q, little q, lowercase q is the momentum transfer. You square it, and in the common notation where time-like vectors square to positive quantities and space-like to negative quantities, Q is space-like because it's the difference between this momentum, light-like momentum, or almost light-like momentum K prime and momentum K. So Q squared is negative, and this capital Q squared is thought of as a positive quantity, is just minus little q squared. And the idea is we want this Q squared, capital Q squared, to be much larger than the mass of the proton. So this again is K minus K prime, the momentum transfer. Now the quantity here that one is very important in this context, the so-called Bjorkian scaling variable X, is Q squared over 2 P dot Q. And that's P is again the momentum of the proton, Q is the momentum transfer. This is in fact the momentum fraction of the struck quark in the model where the process goes forward by one of the constituents whose mass we neglect has momentum X times P, where X is some number between 0 and 1. That's the fractional momentum. And then it absorbs momentum Q, and then XP plus Q, parentheses, squared, on your side squared, should also be a light-like momentum. So this is elastic scattering of this constituent or parton or quark. Yes.
Why does P prime has to be on shell if like there could be many constituents?
So the question is, why does P prime have to be on shell? The answer is it didn't have to be on shell, but we're going to see what it means if we assume it's on shell, okay? We're going to try to interpret that. But the basic observation that was made in this question is that many things can happen. And indeed, when I said the word inclusive, it's precisely that point. We're not going to ask what, quote, really happened to the struck quark. We're just going to observe that with a space-like momentum Q, if a constituent, which is light-like, absorbs it and scatters elastically, then we have something that at the lowest order we can actually calculate. We'll see that that plays an absolutely central role in our description of the process. Okay, so we accept the idea that many, many things can happen, and we're not going to be able to observe, at least at this level in the inclusive cross-section, what it is, but yet we're still going to follow through with this idea. And this was the great idea of Feynman as a way of describing the more mathematically oriented analysis of Bjorkian to describe these experiments. So in any case, you notice that this knowing what X is does not require us to make the interpretation that it's given in this parton picture. X, all you need to know is what Q is and P is. You prepare your protons, and they have momentum P. You prepare your electrons, and then looking at the scattered electron, you can find out what Q is. You now have P and Q. You can calculate X. And then you say, well, you know, if this process went through the scattering, the elastic scattering of a constituent, then X would be related to that fractional momentum. And then you have to go out and say, well, is that just sort of a curiosity, or does that actually give us something? And Feynman realized it should give us something, and indeed it does. All right, there's another quantity, which is called Y, and Y is P dot Q over P dot K. So this, this is an amusing thing. This is the fractional energy transfer, how much energy the electron gives up. And of course, if you say how much energy, you have to say some frame, and that's in the frame, which is the proton rest frame. Okay, because in the proton rest frame, the denominator, which is P dot K, okay, P only has a 0th component, which is M, and P dot K would be MK naught. And then up here, P dot Q is then the energy is MQ naught. So this ratio becomes Q naught over K naught in the rest frame of the proton. And so this tells you how much energy is given up by the electron, at least in the one frame. And you think about it, the electron had to give up some energy because otherwise you wouldn't have enough energy to form this big state of strongly interacting matter that you get out of the hard scattering. Alrighty, so moving right along. W squared, which we said before, is P plus Q squared. The extent that you neglect all the masses involved, this is Q squared, 1 minus X over X. Okay. So it says, interestingly, as X gets smaller, W squared increases. And X getting small is a limit that will be of great interest as the school goes along and talking about the future of the EIC, because these small X, what's happening is that you create these very, very heavy hadronic states. And typically, well, anyway, let me just say that it's of interest. Alrighty, and so a useful identity is, again, neglecting masses. X times Y is equal to Q squared over S. That's sort of neat, actually. All right. Yes, please.
Yeah, I'm looking at the collision of this electron and proton here. So
Yeah.
what energies are we looking at?
What
The energy.
energies are we
Yeah,
looking
at
at?
which energy
At
is
this-
generating the proton and the electron?
This isn't supposed, I mean, when the analysis here, it's not really analysis, this is just kinematics. But we're doing the kinematics assuming that proton mass can just be set to 0. And that all of our particles can be thought of as light-like. It's like a light-like proton just, hitting a light-like electron. So you'd think this only would really make sense when you 100 times the mass of the proton or something. So you have 1% correction if it were M over E, or 10 to the minus 4 if it were M squared or E squared. But the amazing thing that happens, which is again not completely understood even to this day, although it's somewhat understood, is that for these inclusive cross-sections, this works when the energy of the electron is a handful of times, 6, 7, 10 times the mass of the proton. That seems to be enough to make this picture work rather well. And that sometimes goes by the name of precocious scaling, or it did back in the day. And it's still something that's not completely understood. But it's one of those cases where nature, maybe nature was fooling us, but it turned out not to be the case. Nature was like very cooperative. There were reasons for realizing that it wasn't just, it had to do actually not just with the Q squareds and the energy K naught that, or W squared we could achieve, but also the particular range of X. Whoops. How did that happen? Oh, I see. I keep going forward. All right. All right, so the particular range of, now this is the light here. Yeah, the particular range of X that was available kinematically to these SLAC experiments. And they showed the aspects of this which are particularly well described. I don't know why that happens. Anyway, particularly well described by this picture of elastic scattering. To get some idea of why elastic scattering has a lot to do with this, what we really, here's something, this actually, I've kept this slide. As you see here, this goes back to, I believe, the first CTEQ summer school. But anyway, this is nature, it's still true. So here, this is before and after the collision. But it's, we talked about, oh, let's look at the proton rest frame because then Y is the energy transfer. But now let's look at things differently. Let's look at it in the electron's rest frame. So the electron is speeding around, the circle, but it's happy, it's in a vacuum, nothing is going on, it's taking it easy. And here we have that. This is the electron. But little does it know that in the opposite direction of its motion, which has been boosted to zero, comes a proton. Now the proton consists of a bunch of constituents. And as we move very rapidly, the constituents have these fractional momentum P, X times P, so X sub I. And we'll assume that the proton is made entirely of these constituents. You might say, but the constituents are interacting, right? They're exchanging, we know they're exchanging gluons and all this other stuff is going on. It's a beehive of activity. But the thing is, in the electron's frame, the proton is like super Lorentz contracted and time dilated. So all of the characteristic interactions that bind the proton together, again, this is all just words, but not entirely just words, are time dilated. So that in some sense, the proton is acting as though it were frozen as it would go by. Except in this particular case, it doesn't go by, it hits the poor electron. So here are our constituents, and the way to describe them is, well, because of Lorentz contraction, the proton is flat. Because of time dilation, its internal interactions are frozen. And because of causality, because the darn thing is approaching essentially at the speed of light, there's no way for it to send a signal, ahead of time. Watch out, it's like one of these, you could imagine, like an electron proton avoidance system. I think that's going to be in the next, electric car model, but you can't do it because the thing is coming at the speed of light. It sends out a photon. The photon is, hey, you still here? Yeah, where you going at the speed of light? What do you expect me to do? I'm doing my thing, you're doing the same thing. So anyway, so therefore it is, it is in this extent flat, frozen, and unexpected, okay? So now our friend, the proton, hits our friend, the electron, and here's what happens afterwards. The electron is scattered, now has momentum K prime, okay? And here's some stars. These are like soft photons because the electron has a charge, so being accelerated is going to radiate a little bit, okay, at least a little bit. But for the most part, what happens is that all of our partons, which were up here in the original proton, are still here as fragments because they didn't hit the electron. Just one of them hit the electron. But the one that hit the electron has now momentum, say it's the ith parton, it's X sub I plus Q, and it's free. So therefore it has a smiley face. That's free for a little while. But from the parton point of view, it takes a long time, remember, for a hadron to form. Okay, so off our electron goes with momentum K prime. Here's our freed parton, and here are all the fragments. And this is another picture of the elastic scattering. Any questions about this silly thing? Yes,
Even with the electron beam, is that you said it could go like 5G? It would have to be much, much higher than the.
no, so the question was about the energy scales and the original, I don't know, Slack was about a 10 GeV beam, I think, in the original version. Does that sound about right?
But then my question is the proton really coming at you as an electron at the speed of light?
So then the question again, the scale, how for such an electron back then in Slack, how flat, how frozen, how unexpected? Well, apparently enough. But again, very difficult to estimate a priori what the corrections would be. Although that's a subject which is of great interest even to today, because it's these transitional energies. In fact, those scales are part of why people are, when looking forward to the EIC, want to go to the highest energies, but also want to come down to these intermediate energies and just try to figure out what should we be looking at to understand this, as people say, the transition between quark degrees of freedom and hadronic degrees of freedom. Okay. Oh my goodness. I see I'm not going to be getting to that slide 35 or 36, but that is one thing I do want to, okay. So this is the parton model relation, basic parton model relation, which is generalized to give QCD factorization, so-called collinear factorization. So the parton model relation is, in fact, the original form of collinear factorization. And what it says is that for the inclusive cross-section, remember, the inclusive cross-section depends on P and on Q. It also depends on K, but I just didn't write it. Okay, whoops, here we go. We are, yeah. Oh, gosh, it tends to skip twice when I do that. This, okay. No, all right, I'm just gonna wave at it. Okay, the top here, the inclusive cross-section on the left is given by the elastic scattering cross-section times for each variable. Here we're calling it C because it's a variable, but C is like X, it's like Greek X. We integrate over C, which is to say we look at all the possible momentum fractions that partons could take, sum over the partons. Oh. Okay. Oh, we're talking about a 1960s experiment. We ought to use 1960s equipment. Times the probability of finding a parton of type A with momentum fraction C. And if you hit that one, you scatter according to the elastic scattering cross-section. Okay, and that, the claim is, will give you the inclusive cross-section. So again, this is the inclusive, and notice what that is. E of K plus some hadron of momentum P gives K prime, which is K minus Q, plus some state X, which is the strongly interacting state now with momentum, total momentum P plus Q. And here's sigma elastic is again the elastic cross-section, and that, if we know what the electric charge of our parton A is, then we can calculate the lowest order. E plus A goes to E plus A with momentum transfer Q. And again, by saying that this outgoing parton A should be massless, that's what determines X to be minus little q squared, which is also big Q squared over 2p dot Q. So here, again, we want to emphasize this function phi of A in H, where again, H could be the proton, neutron, it could be hamburger, is the distribution of parton A in hadron H, a probability, which should have had an end quote, for a parton of type A to have momentum CP. Oh, actually, there's the end quote. And here's the thing, which is the statement that we know is factorization. this function phi of A and H of C is independent of the details of the hard scattering. It doesn't know anything. It's a statement about the proton. This is the hallmark of factorization, okay? So here's our question. See, this is coming back to the question that you raised. I mean, couldn't all these other things happen? And the statement here is not, oh, we're only taking into account this. Rather, we're saying we're using this to calculate the inclusive cross-section. On the inclusive cross-section, the left-hand side is given by everything. Anything that could happen in that kinematics will happen, and we will count it. On the right-hand side, though, we're using a lowest order, meaning actually zeroth order in QCD cross-section times a parton distribution, where the parton distribution, again, is completely universal. All right. So moving right along. Yes.
May I clearly abuse my role here? So there was quite a lot of discussion, I think last year on that. So right now we are saying that this function is a probability. But of course, very quickly we will figure out that we have QCD and then now objects are infinities and are integrals and therefore yada, yada, yada. We will have a lot of embellishment on that. And at that point, people argue that these functions can become negative, for instance, so they lose their probabilistic interpretation. So I wanted just to see what's your opinion, maybe. How important, if all, the probabilistic interpretation those function is, at least at the leading order?
At leading order, it's important that they be probabilistic. But leading order here means taking this to be the elastic scattering cross-section. Well, what we'll see in QCD, so here there's a complete barrier. You have the elastic scattering taking place, photon is absorbed by a parton, the parton goes its merry way. Okay, and then there's the probability distribution. There's no possible way for those two things to know about each other just because they're not made out of the same things. The only thing that they have in common, sort of, is that the parton be massless, but that you can relax. But the point here is all the strong interactions are in phi. And there is no strong interaction information in this sigma elastic. That, however, as we look at what quantum field theory will say to us, we'll have to give that separation up. We will have to have a sort of ability to organize information about the strong interactions both here and both there, because the strong interactions do exist at these very, very short distances, although because, God, am I running out of time? All right, anyway, because and then we invoke asymptotic freedom to say, we can actually manage this better and things like that. But here, this separation, all the strong interactions are in phi. There, this does have to be a probability, I believe. But then once we give that up, we'll find that we have a certain freedom in how we define phi and how we define sigma elastic. And that very freedom, that freedom is what gives rise to this idea of evolution, as we'll see. Very. Okay, so in words then, the hadronic inelastic cross-section is the sum of convolutions. So this convolution here, although I haven't written it as a mathematical convolution, but that represents this integral that's in the top, the integral over C, of partonic elastic cross-sections with the hadron's parton distributions. So the assertion at the bottom of this, or at least one way of looking at it, is that quantum mechanical incoherence of the large momentum transfer scattering, that's the elastic thing we're describing by the elastic, and the partonic distributions. We multiply probabilities without first adding up the amplitudes. Now, that's something which at the time when people wrote this down said, well, this is a nice theory, but it's kind of dead on arrival because it doesn't respect quantum mechanics. So, what are you doing? But there is a justification, and the justification is that the binding of the nucleon involves long time processes that don't interfere with the short distance scattering. And we will talk about this, how this works in QCD as we go along. Okay. Now, I find myself on slide 14 of about 35 slides. But we can, I probably should stop very soon. Put it that way.
I think we can do 10 minutes.
Oh, okay, all right. Oh, all right. So anyway, so here, from this point of view, you can say, okay, well, what is this elastic scattering? And this just gives the formula for those that are defines S, which is the usual, the Mandelstam variable for the hadronic system, the hadronic system with the electron. Remember, this is electron parton scattering. So it says, okay, I started with Cp plus K, take the square of that, I'll call that S, there's a U and a T, the T is the minus Q squared. And when you calculate this, you find that at this lowest order, our cross-section, the elastic scattering cross-section has a Dirac delta function which fixes this C to equal X. Now at higher orders, we'll see that indeed this is not the case and that we will get a true integral over C. So to analyze deep elastic scattering in general terms, we'll introduce a more general notation, not just talking about the cross-section, but rather of the so-called structure functions, which I had hoped, well, we'll just do it the next time. I think it's.
You define the omega in the left on the left hand side.
Oh, the omega, yeah, this is the typical Lorentz invariant form, which doesn't mean I shouldn't have defined it. It's just the energy. So in other words, it's the absolute, if you're neglecting the mass of the electron, which is an excellent approximation, it's the absolute value of 3 momentum in natural units. All right, so here's the conventional picture for these distributions. And I can't help but say, it's sort of interesting. I mean, again, this quantum mechanical incoherence or the idea, the kind of buzzword for factorization. There are no interactions between the outgoing scattered quark and the rest. So whatever else you would have thought, oh, well, these guys, they notice, right now, this proton has been together since nucleosynthesis in the early universe. That's bounced around, it's spit out of supernova, eventually it makes its way to Earth. These same 3 quarks, well, calling them the same is like anthropomorphizing, but I've always found anthropomorphizing is a good idea when it comes to quarks. They've been together all this time, and suddenly they hit an electron. You come back, right? So don't they throw out gluons and all that kind of stuff? Well, yes, they do, okay? But those interactions between the outgoing scattered quark and the rest don't contribute to the inclusive cross-section. And we're going to argue as to how we can think about that intuitively and on technical terms. Well, basically, intuitively, the idea is the scattering takes time like a time which goes like 1/q. And the interactions that form hadrons are much lower than that. If Q is much, much larger than what we call lambda QCD. And so everything that happens once the scattering takes place, we'll think about it as saying, actually, if we sum inclusively, what actually happens is we fix the scattering to take place very well-defined 1/q region in the amplitude, quantum mechanically speaking, and in the complex conjugate amplitude. And once we determine that an interaction has taken place, which we can do by looking at the lepton, the scattered electron, then everything else that happens after those interactions has to sum up to a probability of 1. We're saying we're accepting anything. That's the magic of this word inclusive. If we say that, okay, at time 0, in the amplitude and the complex conjugate amplitude, there was a hard scattering, then everything that happens after that doesn't matter for the inclusive cross-section. It's there, it's very complicated. If you start looking at the details, you may find ways of calculating certain parts of it. But if you don't look at any of the details, it's just a set of probabilities that sums up to one. It doesn't matter what theory. And that's what enables us to factorize this parton distribution from the elastic scattering. So note one thing is that cross-section is like an area. So for one parton, you have an area for momentum transfer Q of like 1/q squared. And the area covered by single partons at 1/q squared is like the parton distributions divided by q squared, because this is kind of like the number of partons at this x. But for this picture to work, we should have that this parton distribution divided by q squared, the characteristic area that the electron sees when it bounces off something, should be much less than the radius of the proton, or here it could have been n. So if your parton distributions get really big, then you may find that a single parton covers the whole size of the nucleon. Or intermediate, they begin to interfere with each other. One parton's in front of the other, so you don't really know what you're looking at. And this concept is called saturation, which will be a subject that will come up a number of times, of course, of great interest to the EIC community. All right, what makes QCD different? Well, here is, well, okay, really, all right, we're almost the end here of this. Oh, this is actually an okay place to start. Let's just stop. I think we've gotten to the parton model, at least portions of it, and we'll just continue to develop these ideas as we go along. People can ask for a little bit more in the discussion section at a later time. So thanks very much for sticking with me.